make sure to mute the YouTube video because otherwise I hear myself like a minute after I said something on Zoom. How have your other classes been going? Have you guys been able to have class pretty well? And make sure to there we go, you see. Just like 30 seconds delayed. So, oh yeah, let me just share that stream. Okay. Uno momento, por favor. All right. So anyways, okay, so you guys we're talking about chapter 8. You can since there's just 4 of us, why don't you unmute your mic and we're gonna have just a little conversation. It's meant to be you guys are supposed to share. So can you actually, why don't we take turns then? We'll take turns. We'll take turns in order of actually whenever. Somebody want to go first? So what did you read in chapter 8 that you found interesting? Was there anything remarkable in chapter 8 that you want to talk about? Anything a little strange or interesting?
Yeah, I really liked all these different theories of how the universe grew from the singularity that they're all postulating it started from.
Okay.
I really thought the cold universe beginning was very interesting. How it was, don't remember whose idea it was, but it the universe was very cold up until it grew to a certain size, and then it finally started to. It was like super cooled.
And then, so yeah, he mentions that, right? I remember reading that too. Let's see. That's kind of a strange idea, though, isn't it? That it's so hot afterwards. I think maybe I don't really remember that it was super cool before. Actually, maybe hold on a second. I think maybe you're thinking of something else. Actually, yeah, I think I know what you're talking about. So it's like something that is super cooled. And have you ever seen water? Like a bottle of water that you stick in the freezer
Yeah.
and actually you take it out of the freezer and it's not frozen. Have you ever seen that?
Well, my water usually does freeze when I stick it in the freezer.
Right. Most people, you have normal water, right? But actually, you know what? This is so fun. Let's just do something random, if you guys don't mind. I'm gonna actually show you guys something because I think what you want to understand is you were saying the universe is really cold, and I actually can't imagine that the universe is really cold. So let's just try something for a second. I'm going to go ahead and click my my Google here, and I'm gonna actually go over to this tab here, and this is supercooled water. Okay, so the idea is that you take, let's watch an ad first. Okay, I have the sound off. I don't know if you need any sound for this. Okay, so the idea is you take a bottle of water and you put it in the freezer, and you might need a few bottles of it. It turns out if there's any little impurities in the water, even bubbles actually, then they can cause it to freeze. But you see this person has a bottle of water, and now you'll notice that it's actually freezing now, right? You see the propagation of the freezing wave.
Yeah.
Right, through the bottle. Have you ever seen anything like that before?
I've seen it portrayed in a lot of films before.
Okay, this is something you can actually do at home, but it's difficult to do it with tap water because you actually really need to have purified water. Um, so it's probably like a bottle of water or distilled water. But actually, at the moment that they pour it out, the disturbance of the water causes it to begin freezing. And so what you see, do you see how it just suddenly turned into a solid? Isn't that crazy? That is so cool. That's awesome. Okay, and then you can see the last little bit inside the bottle actually froze as well. So what's the state of the water before it freezes? Do
Look,
you know what
since
it's called?
well, if you ask me that, I feel like it's called something a little different than just a liquid.
Well, it's a liquid, but it's cold enough to freeze, right? So it's called supercooled, right? So you've gone past the cooling, the point where it should normally freeze. This is cute. That's actually cute. Bunch of kids doing that. Okay. So now you can actually do the opposite. You can put, actually, this is kind of scary, by the way. This is something you want to be really aware. This is dangerous. I'm about to show you something dangerous. Do not do this at home, right? Do not, one more time, don't do this. I know it's intriguing and you're like, let me try that, but don't do it. It's really dangerous, okay? But I want to do superheated water. Now, if you put water in a microwave for, a couple minutes, it starts to boil, right? But what if you put it in the microwave and then you accidentally put it on like 10 minutes or something, right? That's way too long. And so what happens is you go way past the boiling point. But if the water is clean enough and the container is clean enough, then you can actually get the state of water where the water is heated way above the normal boiling point. Okay, so actually, these guys are awesome. Do you guys like Mythbusters? Anybody else like Mythbusters?
Yeah, I like them.
Yeah, they're so awesome. I love them. They're so cool. Okay, so actually I can't see anybody. Okay, so Leonie, do you know Mythbusters? Or who said that? Is that Leona?
Leona said that, yeah.
Okay, all right. So if you haven't seen them, they're pretty awesome. They do all kinds of fun experiments. Let's see this experiment. So exploding water. What is the reason for this exploding water? You might want to write it down in your notes. Superheated water, right? So actually what we're doing right now may seem gratuitous, but it's actually connected to something that you read about in chapter 8. So I want to make sure you understand. So we talked about supercooled water, where the water is cooled past the freezing point, and then a sudden disturbance causes it to begin freezing, right? So now you're going to watch water that has been heated past the normal boiling point and then is suddenly disturbed.
If you overheat water in the microwave, you may take the cup out of the bowl and then the water is going to explode in your face, injuring you or burning you in some horrific way.
We're going to time how long it takes to bubble. After a little research, Adam and Jamie know that the only way water could explode is if it's being superheated, that is, heated beyond boiling point, without actually boiling. Tap water always boils because it has impurities. Distilled water has no impurities. That means no boiling. They put 2 cups of water in the microwave, 1 distilled, 1 tap. When the tap water boils, they'll know that the distilled water has become superheated. Just dropping in a sugar cube should make the boiling process happen instantly and violently. Erupted, it left the container. Yeah, quite a bit of it. If someone were holding the cup, they would definitely have severe bleeding. But if straight tap water can't be blocked, how likely is it that people will be scalded by exploding beverages? On your average day in your average house, it's not very likely. However, with the hundreds of millions of people using microwaves every day to boil water, reboil water, I'd say it could happen a few times a year around the world. Myth absolutely true.
Okay, so did you understand what happened? What actually happened? It was not regular water. What kind of water was it?
Just totally pure H2O.
What was it? Low impurities, right? So it was like distilled water would be a good stuff to try. So I just said don't do that at home, but if you knew that it was going to explode and you wanted to try it at home, you could try to do it. But just be very careful because it really does work. The two things you need are a container that's very clean, that has no dirt on it, because dirt will actually cause boiling to happen too, right? So it's kind of a neat thing. You might actually ask the question, it's raining outside, right? Or it was raining earlier. Why does rain happen? Do you guys know why rain happens? I know you're like, why? What are you talking about? Random stuff, but it's all the same. It's all connected. What I'm telling you right now is all connected, everything. Anybody know how rain forms?
Does it have to do with the pressure up in the clouds, and when the pressure reaches a certain point, and then it'll finally start a downpour?
Well, it's not the pressure so much, actually. So there's water moisture in the atmosphere all the time, all the time. There's water, humidity, right? That's humidity. There's water moisture in the atmosphere all the time. But are there droplets of rain all the time? Or clouds all the time?
Yeah, no, not all the time.
Yeah, so what is the difference? You said pressure, but it's not the pressure, it turns out. I mean, it is part of it, but it's not the most important part. Anybody know? Why do the clouds form higher up in the sky? And you were thinking pressure, right?
Yeah.
But it turns out it's something else. What happens as you go higher to the temperature?
It gets really
Does it go up
cold,
or go down?
really warm. I think up there it's colder.
It gets colder, right? So if you go up to the top of a mountain, sometimes you might have noticed how cold it is at the top of the mountain. So the higher you go, the colder the atmosphere becomes. And at some point, if you give the water a nucleation center, then the water can condense out of the gas vapor. So raindrops can form from around, each one will form around a little dust particle. That's not always true. It turns out fog is just the just straight water, little tiny droplets of water that are condensing out of the gas. But if you look at raindrops, most of the raindrops are going to have little particles inside of them. And the particles allowed the initial water molecules to have a place to condense. So condensation is aided by the presence of little impurities or little tiny condensation centers. So if you've ever caught like a bunch of rainwater, you might have noticed that there's some silt at the bottom of it. And that silt, that very fine dust, is actually coming from the rain itself. It's not from the air, it's from the rain itself, and which is kind of a funny little thing. All right, so why are we talking about all these things, right? So we just talked about superheated water, supercooled water, and now raindrops. But all of them are showing you something happening very quickly, right? Actually, sorry, not all of them are happening quickly, but all of them are changing phase. So the key word, the connecting idea between all of these is the word phase change, right? So write down phase change. And sometimes the phase change can happen rapidly. So the word is phase change, right? So what does phase change mean? You know what I need to do? I just realized I need to control my video camera, because my video camera is trying to autofocus on a face, and I'm looking at paper. So I finally figured out why. I need to get the app and tell it to stop trying to autofocus. Anyways, a phase change, what's happening? It changes from one phase to another, right? Obviously, phase to another. And what are the phases we're describing, right? We're talking about solid, liquid, and gas, right? These are the normal phases. Now, there are other phases, right? What's another phase? What's another phase of matter? These are phases of matter. Phases. Yeah, that's right. So we can put plasma down here. Actually, I think that one's kind of cool too, and we might as well talk about it. So these are phases of matter, right? And a phase change is when you jump from one to another, right? And why does that happen? Well, it turns out because energetically it's favorable. In some way, there's an energy release when that happens. So actually, Hawking throws this in, and I think it's actually a pretty important idea. He says that if you imagined the universe expanding, and what happens to the temperature as it expands? Did you hear that?
Down.
It gets cooler, right? But when he said the word supercooled, you want to understand that he didn't mean that it was cold at all. He meant that it was cooled beyond the point where it would normally do a phase transition, but it hadn't yet. And so what does it mean, right? So if you take something that's very hot, right, very hot, and you expand it, right, you expand it, what happens to it? Well, the larger it gets, the cooler it becomes. And what you expect to happen is that this material that's in here might change phase, right? So let's say it's a hot plasma. As you expand and cool, you might expect it to become little gas particles, right? But they wouldn't just, so the process of becoming is called a phase transition, right? The becoming from one material into another is a phase transition. If it doesn't make that phase transition, if phase transition doesn't happen when you expect it to, you could have a supercooled state, right? Supercooled, what does that mean again? It doesn't actually mean cold. What does it mean? Colder than expected, right? So it's like when you cool, what temperature does water freeze at?
0 degrees Celsius.
Yeah, 0 degrees Celsius, right? So imagine that you cooled, and again, distilled or very clean water is going to make this easier. But you go below 0 degrees, and then any sudden kind of jostling or any sudden kind of force is going to cause it to instantly solidify. So supercooled means it's gone beyond a state where you would normally expect it to change phase. And then it doesn't take much. All at once, it does a phase change, right? So then you can get a sudden phase change can occur. And what always happens whenever, whenever you have a phase change, what's going to happen? The matter is going to rearrange itself into a lower energy state. So what does it do when it undergoes a sudden phase change? Always. What does it always do? If the new phase is in a lower energy state, then how do you form the new phase? You have to release energy, right? Releases energy. So whenever you have this sudden phase change, there's a release of energy. So Hawking was trying to describe how that might happen, right? How would that happen in the early universe? He said, if the universe is expanding, you might expect the particles to form all at once. But he said that maybe, in fact, you can get the supercooling. But then eventually it does, actually. It does, in fact, change phase. But in the process, it's going to release energy along the way. So let's find that section, actually. And now maybe it'll make more sense for you if you look at this. So the universe is not expanding I'm looking at page 129 down at the bottom. This is, I can read to you guys. I'll switch to this here. I'm going to read to you, right? It's like bedtime stories. If you guys are feeling sleepy at night, you could just turn this on and I'm just kidding. Okay. I can't see your faces. It's disappointing, you know. You guys want to show me your faces? No, you don't have to show me your faces. It's fine. Anyways, you guys are probably in your pajamas, right?
Exactly.
Yeah.
Okay. All right. The universe is not expanding in an inflationary way today. You need to know that, right? You need to know. The inflationary process was incredibly rapid, right? More rapid than we even, it's crazy fast, right? So it was this stage where the universe rapidly expanded, and we call it the inflationary phase, and then it slowed down, right? And then it slowed down. Why? So the universe is not expanding in an inflationary way today. Thus, there has to be some mechanism that would eliminate the very large effective cosmological constant, and so change the rate of expansion from an accelerated one to one that is slowed down by gravity as we have today. In the inflationary expansion, one might expect that eventually the symmetry between the forces would be broken, just as supercooled water always freezes in the end. The extra energy of the unbroken symmetry state would then be released and would reheat the universe to a temperature just below the critical temperature for symmetry between the forces. The universe would then go on to expand and cool just like the hot Big Bang model. But there would now be an explanation of why the universe was expanding at exactly the critical rate and why the different regions had the same temperature. Okay, so did you hear something more now?
Yeah, so it was more like not the actual temperature that the universe had, but the properties it was acting under until
right.
it
Well, so
returned.
he's trying to explain this weird thing that we observe, right? That somehow, first of all, before this, in the inflationary period, one of the things he does talk about, we just skipped right over it, is that he believes the forces of the universe are all unified, right? That one of the goals of particle physics is to achieve a state like the early universe and to show that the forces that we consider separate, right, the electromagnetic, the strong nuclear, and the weak nuclear force, are actually the same force. They're manifestations of the same force. But what's happened is they can't be distinguished when the universe is this hot mess in the very early universe. It's only possible to see them as separate in this cooler state that we're in, right? The cooler universe state. So, and then actually let's keep reading, because actually I think now it'll make more sense. In Guth's original proposal, the phase transition was supposed to occur suddenly, rather like the appearance of ice crystals in very cold water. The idea was that bubbles of the new phase of broken symmetry would have formed in the old phase, like bubbles of steam surrounded by boiling water. The bubbles were supposed to expand and meet up with each other until the whole universe was in the new phase. The trouble was, as I and several other people pointed out, the universe was expanding so fast that even if the bubbles grew at the speed of light, they would be moving away from each other and so could not join up. So this is a really fun idea. Do you understand what he just said?
So all the areas that would have been releasing the energy from going into the warm state never would have, like all the bubbles made never would have quite met up, just because the rate of the universe expansion would just they'd never be allowed to play catch up.
Right. So, but what are these little bubbles? Where are the bubbles? Where is the bubble? What bubble are you talking about, right? What bubble is this? Well, actually, we're in a bubble.
Galaxies, galactic clusters.
It's not a galaxy. No, it's bigger than that, probably. But we are in one of the bubbles, right? He's saying
whole universe. Oh.
This whole universe that we observe may be a bubble. I'm not saying that that's the case, but do you understand what that might mean?
Yeah.
What does it mean?
It could mean there's.
How big is the universe?
There can be a whole bunch of universes out there.
There could be, absolutely, right? We are just one bubble, perhaps. We don't know. We don't know the answer to that question. And so it's just something to consider. But the problem is that if we can never see it and we can never communicate with it, then does it even exist, right? I mean, we don't know. We could just hypothesize that it exists, but it's basically, it's untestable, right? This idea that there's another universe or many, many universes that might have formed out of the bubble of this inflationary early universe is not really testable. So we have a problem, right? It's not science anymore. It's more like a neat story to tell. But it is a fun story. It's a very fun story. And I think you should consider it. But the key thing that you heard was the supercooled state. there was a sudden transition from this place where all of the forces were unified to a place where we have a more normal kind of universe that went on to expand, and it couldn't expand at the same rate anymore, right? This is his explanation for why it changes from the inflationary to just expanding, right? So he needs to figure out a mechanism. This is a mechanism, right? A phase transition occurs, and in the process releases energy, which reheats the universe, but not enough to get back to the original state, right? You can't ever get back to the original state. When you take superheated water and then you drop something into it, it explodes violently. Well, you can't get it back to the liquid state again, right? You've disturbed it and changed its phase. It doesn't just spontaneously go back the other direction. That would require a gain of energy. And so it just doesn't happen. Spontaneous changes only occur in one direction, right? To lower energy, which is an important idea too. Okay. So anyways, this is kind of a fun idea. So actually, he goes on and talks a lot. Actually, so let me ask you guys, what can I do? There's something about, he goes to the Soviet Union, he goes to Moscow. In October 1981, I went to Moscow for a conference on quantum gravity. So actually, it's kind of cool that these ideas have been around for a while. There are some things in here that I wanna let you know that as a physicist, I feel like he's pulling a little bit of sleight of hand on you, but I do want to talk about it because it's fun. It's really interesting. Let's see. Okay. Oh, okay. So this is kind of a fun thing. So he went to this conference. I gave a seminar. How do we make this more interactive? Actually, I've been trying to play around with ways. This course is meant to be more interactive, and here I am talking a lot. Lonnie's talking a little bit. Leona, we heard from a little bit. But actually, there must be a way for us to interact more. And what I'm going to do, I think, is this week, part of your participation grade, like I've been doing with some of my other classes, is to get involved with each other and have some discussions. This is meant to be a course on discussion. So let me go back to our website for a second. I haven't done anything on your Canvas, but let's go ahead and go here. There's a discussion section on Canvas, and there's really not much here. YouTube videos. Oh yeah, these are actually kind of fun. These are fun. These are actually pretty fun. Stephen Hawking train ride to the future, kind of cute. And then general discussion, there is nothing here. Okay, so what I want you to do as part of your participation points this week, so I will give you a quiz like usual. I haven't made it yet, but I will give you one. And then let's see, so half of your points will come from this quiz that I give you. And then the other half are going to come from your discussion section. Okay, so I don't know if you can click this or not. It doesn't seem to work. Okay, so what you can't really, I don't know why, maybe you guys can't see these then. Oh yeah, you can see this. You can reply. Okay, you can reply, but you can't. Okay, so general discussion, you can reply here too. Okay, cool, that works. Okay, so, or you can make your own discussion topic, right? So what's a cool topic? Let's see, phase change. Phase change explains the bubbles forming in the inflationary universe picture. They slowed the process down. Okay, well, anyway, so what you're going to do for 5 points is you're going to post a discussion topic or a response to it. Okay, so I'm going to look for your participation by Wednesday, and that way I'll give you your other 5 points. So actually you want to try to pick something that's interesting to you. It could be something, actually try to make it something in chapter 8. something related to chapter 8. So you could actually make a note, right? This is chapter 8. Chapter 8 material. Okay. Do you guys understand what I'm asking you to do? I'll go ahead and make it an assignment, or not an, yeah, I guess I should make it an assignment. But I'm telling you verbally that half of your participation points come from making a discussion topic or responding to someone else's discussion topic. Okay. All right. Make sense? Anybody? Yes?
Yeah.
No? Okay. All right. We have a chat too. Hi. Good morning. Good morning. Good morning. I miss seeing you guys. Anyways, okay, so we're here and we're healthy, right? Everybody's healthy? Nobody's got a cough? I don't hear anybody coughing. Anybody coughing?
No, but I have allergies, so I've been sneezing.
Oh no, yeah. Actually, yeah, one of my friends has been sneezing relentlessly because of the allergies.
Oh no.
Yeah, you too?
Not relentlessly, but at least once a day.
Oh, really? Okay, and you're kind of stuffed up or something?
Yeah.
Okay, all right. Well, does the rain help? Does it take all the particles out of the air?
Yeah, actually, I haven't thought about that, but yeah, it has
Yeah,
helped.
you could take a walk outside in the rain. Mary and I went walking in the rain last night. We got all wet. I mean, we had umbrellas even, but we still got wet. But it was coming down pretty hard. Okay, so keep going. I like this part because he gets embarrassed. I think it's kind of funny. He says, in October 1981, I went to Moscow for a conference on quantum gravity. You guys have the book. This is page 130 that I'm reading. After the conference, I gave a seminar on the inflationary model and its problems at the Sternberg Astronomical Institute. Before this, I had got someone else to give my lectures for me because most people could not understand my voice. Did I tell you guys I met Stephen Hawking? I don't know if I met him really, but he was in the elevator with me at UCSB. And actually, he was in his chair, you know. It was after he couldn't walk anymore. But he would come to UCSB to give talks actually at the Kavli Institute of Theoretical Physics. And he was in the physics building actually visiting. And I was a physics student in the 80s, you know, at UCSB. It was kind of cool. And he gave a talk. Actually, I went to one of his talks. Kind of neat. Anyways, but there was not time to prepare the seminar, so I gave it myself with one of my graduate students repeating my words. It worked well and gave me much more contact with my audience. In the audience was a young Russian, Andrei Lind. This is, guys, that's a famous name, by the way, now, from the Lebedev Institute in Moscow. He said that the difficulty with the bubbles not joining up could be avoided if the bubbles were so big that our region of the universe is all contained inside a single bubble. Okay. In order for this to work, the change from symmetry to broken symmetry must have taken place very slowly inside the bubble. But this is quite possible according to grand unified theories. Lind's idea of a slow breaking of symmetry was very good, but I later realized that his bubbles would have to have been bigger than the size of the universe at the time. It showed that instead the symmetry would have broken everywhere at the same time rather than just inside the bubbles. This would lead to a uniform universe as we observe. I was very excited by this idea and discussed it with one of my students, Ian Moss. As a friend of Lynn's, I was rather embarrassed, however, when I was later sent his paper by a scientific journal and asked whether it was suitable for publication. I replied that there was a flaw about the bubbles being bigger than the universe, but that the basic idea of a slow breaking of symmetry was very good. I recommended that the paper be published as it was because it would take Lynn several months to correct it, since anything he sent to the West would have to be passed by Soviet censorship, which was neither very skillful nor very quick with scientific papers. Instead, I wrote a short paper with Ian Moss in the same journal in which we pointed out that this problem with the bubble and showed how it could be resolved. Okay, so, all right. So anything, there's so many things in this chapter, and then, you know, he does come up with some other ideas. We're talking about breaking symmetry when things, the phase transition between a universe where all the forces are combined, right? A single grand unified force, and then they break, right? They stop being the same, and they have separate kind of avenues in which they act. Okay. Blah, blah, blah. Okay. There's no phase transition super cold. Okay. So, you know, let's not talk about that one. There was something else I wanted to talk about that. Okay, here we go. So he talks in this chapter a little bit more. In order to predict how the universe should have started off, one needs laws that hold at the beginning of time. Right? Everybody hear that? The beginning of time at t = 0. If the classical theory of general relativity was correct, the singularity theorems that Roger Penrose and I proved. So by the way, everybody knows that he worked with Roger Penrose, right, on these singularity theories, which lead to concepts of the Big Bang. I proved that the beginning of time would have been a point of infinite density and infinite curvature of space-time. All the known laws of science would break down at such a point. One might suppose there were new laws that held as singularities, but it would be very difficult even to formulate such laws at such badly behaved points. No. And we would have no guide from observations as to what those laws might be. However, what the singularity theorems really indicate is that gravitational field becomes so strong that quantum gravitational effects become important. Okay, but that's kind of a key point, right? That the early universe with such a tiny little size, the gravitational fields become as strong as the other forces involved. Okay, so as we shall see, it is possible in the quantum theory for the ordinary laws of science to hold everywhere, including at the beginning of time. It is not necessary to postulate new laws for singularities because there need not be any singularities in the quantum theory. Okay, so when we get to the quantum theory, finally, we will realize that you can't actually have a 0 dimension quantity, right? It's going to be a finite quantity. And this is what the solution, this is really why all of these problems that I don't like about black holes are going to go away. But they don't exist yet. So anyways, he goes on a little bit later to talk about quantum theories. So we don't yet have a complete and consistent theory that combines quantum mechanics and gravity. However, we are fairly certain of some features that such a unified theory would have. One is that it should incorporate Feynman's proposal to formulate quantum theory in terms of sum over histories. Okay, he just throws it in there. In this approach, a particle does not have a single history as it would in a classical theory. Instead, it is supposed to follow every possible path in space-time. With each of these histories, there are associated a couple of numbers, one representing the size of the wave and the other representing its position in the cycle, its phase. Okay, so I do want to break into a new topic, and I want to talk about Feynman's path integral. Okay, so let me go back to my Wikipedia page. I was just reading this critique of Wikipedia. Wikipedia is not the bomb for everything, okay, but I will tell you that it is pretty awesome for science and especially for astronomy and physics. I mean, it's just so good. So this article is about a formulation of quantum mechanics. Okay, for integrals along a path, that's something else called a line integral. Okay, the path, can you guys read this? Is it easy for you to read or hard to read? Should I zoom in?
Well,
Anybody?
It is definitely a little small.
A little small? Okay, so let's go ahead and, is that better? No, that's not better. Is that better?
Yeah, that's way better.
Okay. So actually, why don't you look over here? Can you guys write this down? This is so beautiful. Oh, God, I love this. I wish I could teach you this. This is so cool. This is a really beautiful equation. Actually, I can tell you about it, right? Why don't I tell you a little bit about it? So you see the symbol right here? Who knows what that symbol represents?
Is that omega?
No, it's
Or
called
no.
psi.
Psi.
Remember psi?
Nope.
I told you what it is. What is it?
I don't remember.
It's called the wave function, right? And it represents all of the possible states of something, anything, right? Whatever it happens to be. And you can see this parentheses with t in it. So this is a time-dependent wave function, right? That's what it's saying, that something that depends on time, okay? So there's a bunch of symbols. There's that letter I. Who remembers the letter I? What does I represent? Anybody?
Imaginary.
Imaginary. You might have wondered why I use that as your password today. Does anybody know why? It's in this chapter. Why did I use the word imaginary?
Imaginary time.
Exactly. Thank you very much. Okay. If you missed that point, Hawking describes something important. It's a very cool trick. It's a trick. Well, it's not a trick. It's a mathematical tool, but a very clever tool that is being used in quantum physics to solve problems. And that is, instead of using regular time, use imaginary time. And I'll show you what happens in just a moment. Now, we're not going to do all the math because I haven't done this in years and you don't have the skills yet. But if you take a look right here, I did show you this symbol right here. This is called a ket. And if you flip it over, it becomes a bra, and together it makes a bracket. And that's how you calculate quantities in quantum physics. So this right here, you don't have to know it, but if you want to write down, I'll write it down for you. Actually, let's write that equation down. So you wrote down, let's write down that equation. Okay. This is some fun stuff. Oh my gosh. This is some fun. I'm writing down the equation. You write it down right now, and then I'll describe what's going on. Okay, so I'm going to switch back to this screen for a moment. Okay, so here's our equation. This is our wave function. You might recognize Planck's constant. This is actually Planck's constant divided by 2 pi. But anyways, this is Planck's constant. And it turns out to be part of everything that we do in quantum physics. And this is really famous. This is a famous quantity. This is called the Hamiltonian operator. And I'm showing you this not because we're going to do anything here, but just one day some of you are going to go on and do more, and you'll finally be able to say, oh, that's what that is, right? An operator is the way that we calculate quantities inside of quantum physics. So if I say to you, so what is the Hamiltonian operator? And so because you're my students, you need to know something. The Hamiltonian operator tells you about the energy of a system, the energy of a system. So if I were to write down another, I could write it in a different formulation. If I act on a wave function with an operator, what it tells me is the energy of that wave function. But I can't actually get energy out right away. In order to get the energy, I have to sandwich it between this thing, right? So this one is called the bra. I think I've told you that before. Can you see that psi of t, and then my Hamiltonian operator, and then this is called the ket. And it's kind of a cute little tool, but the idea is that when you put it between these two things right here, then you get a number. You actually you measure, right? So somehow putting this between, yeah. Am I really showing you this? Why not? I'm going to show you a theorem. If this is just a number, then it can come outside and you get E, and then you have the probability. Okay, I'm going way too far, but why not? This is fun. I like this. I haven't done this in years. So now I'm going to tell you something crazy. This is the probability of the particle or whatever existing in any possible state, right? And when you put a bra with the same thing ket, it turns out something delicious happens. It's equal to 1, right? Because it's like, what's the probability of the particle existing somewhere? And the answer is 1, right? It's 1. So since this takes everything into account, any possible state, and here any possible state, eventually something happens. You know, the particle exists somewhere, and therefore you have to get a 1. And so you just get the energy of the system, okay, the energy of the particle. So does anybody remember something called the charge conjugate? Remember that concept, charge conjugate? What does it have to do with? Okay, you might have forgotten imaginary numbers, right? Imaginary quantities, right? So if I have a number a plus ib, right? That's the number c. That's a complex number. What is the charge conjugate? And we put a star above it, right? And the answer is a minus ib. This is the complex conjugate of this number. So the letter I represents what? The square root of -1. This is a number that you and I cannot ever observe. It's not observable. But if you do get in a situation where you have I squared, you get -1, that's observable, right? So I by itself is never observable, but is used in physics and in quantum mechanics especially to describe a system, right, of some kind. So when you talk about this bra, it turns out that the bra is the complex conjugate of the ket. Okay, that's how you get them. That's how they're connected to each other. Okay, all right. So yeah, that's way too much. You didn't need all that. But anyways, hopefully you got something out of that. The Hamiltonian operator gives you the energy, and the Hamiltonian operator is part of the Schrodinger equation. Okay, so back to the screen share. Sorry, back to the screen share. Okay, so I wanted to share with you. This is how we find things out, right? The way you find out about a quantity, a quantum mechanical quantity, is by acting on that quantity with an operator. Okay, all right. So let's read this definition here. The path integral formulation is a description of quantum theory that generalizes the action principle of classical mechanics. It replaces the classical notion of a single unique classical trajectory for a system with a sum or functional integral over an infinity of quantum mechanically possible trajectories. Wow. Does anybody know what that means? Okay. So what we're going to do is we're going to try to simplify this idea. You need to know what we're talking about. Who invented this? Feynman, Richard Feynman. And it was a very clever idea. And it actually comes back to a concept that's kind of more matter of fact. And actually, you know what? I feel like I need to just stop and show you guys this. I don't think I did before. Is let's say I have a particle, a quantum mechanical particle. It's at position A, right? Position A. It begins at position B. I'm sorry, it begins at position A. And then it's going to go over here to position B. And so how does it get there? And if this were classical physics, in classical physics, I could draw a path that the particle travels on, right? For example, maybe it's, you know, this more direct, it's supposed to be direct, sorry. Or maybe it's like, you know, you threw a rock and it fell on an arc, right? But there would be a single path, right? Classical physics, a single, definite path. But that doesn't happen with Feynman's path integral, right? Path integral. he describes a quantum mechanical, this is a quantum particle, right? Quantum physics idea now. That when you go from point A to point B, there's still two physical places, but it turns out that you don't go in just one way, you go every way. And it's really every way. And I know that seems impossible, but it turns out that is what you have to think about. Okay, so what does it mean to go every way? So here is a picture to look at. Look at that picture, right? These are just three of the infinitely many paths that contribute to the quantum amplitude for a particle moving from A to B at time t0 to t1, right? But here's the idea. Not every path is equally likely. Some paths are more likely than others. And so Feynman showed that even though any path is possible, it turns out that you will get a higher probability path, right? And it turns out it becomes more classical looking after you do the calculations. But really, this idea is that any possibility can happen, but there are more likely possibilities, and they will have more paths kind of present there. They will tend to reinforce each other, and therefore, when you do the integral, they won't cancel each other out. So think about the concept of interference, for example. He would say that when you have these very diverging paths, right, that they would tend to cancel each other out. They would not end up being a big contribution. That it's only the paths that are kind of more likely, when you add them all together, that you get the most likely, a path that is more likely. Okay, so blah, 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 blah. Okay, so this is a long article. You could go find it yourself on Wikipedia. I want to go ahead and search for what Hawking describes, and that is the concept of imaginary time. Okay, so I want you to look at this. Again, this is more complex than we can handle, but I want you to read what it says. This is called a Wick rotation. You don't actually need to know that, but it is a very common to perform a Wick rotation from real to imaginary time. So why would you do that? Well, something really cool happens. Okay, so we can jump to the next one. So when you do imaginary time, it's still too hard for me to read. Okay, I think I can kind of, maybe I can get the idea. Imaginary, no, not yet. No, no, I can't see it yet. I can't see it, no. Oh, I guess that was it. Okay, so if you do imaginary time, what happens is it simplifies the equation, and it makes it so that, okay, here, this is actually it. Blah, blah, blah. Here we go. Note the sign chain, blah, blah, blah. Okay, okay. Where the change is, so imagine, you could write this down. Imaginary time changes the space-time geometry from Lorentzian to Euclidean. And you'd be like, what the heck is that? Well, what's Euclidean? Euclidean space, I don't know, what's the definition? Let's see, the definition of Euclidean space. Euclidean. Euclidean, what's Euclidean? Euclidean space. What's Euclidean mean? Euclidean, why do I know? Why do I want to know that? Euclidean, anything? Nothing familiar at all. This is so confusing. What's Euclidean? Oh, wait a second, wait a second. In Euclidean space, look at this. In Euclidean space, you can see this. Anybody recognize this? The Pythagorean theorem. So what happens when you transform to imaginary time is that time becomes exactly like space. And that's actually one of the comments that he makes in the chapter. So actually, that's probably what I would write down, is that the transformation, so Feynman's path integral says any path is possible, right? but there will be lots of paths on the higher probability that will tend to reinforce each other and give you a higher probability along a more direct path. Even though these ones are possible, they're less likely than the ones that are more direct. Okay, so Feynman would have described, you know, when you take the sum over all possibilities, you still get something kind of probably closer to a more classical picture, because they tend to reinforce each other. But all of them are possible, right? This is an important concept. So I'll make my dots bigger. Okay, so back to what I was just telling you. With imaginary time, there's a cool trick, right? Imaginary time, what happens, right? Time becomes like space. You can't tell the difference. And so it's Euclidean, right? He used that term. Oh no, we use that term, but I think he does too. Let's see. Oh yeah, he does. He totally uses it. Okay, here we go. So actually he makes this point right here. I just want to try to, I actually don't like that he did this, but he's trying to, you know, introduce people who are not familiar with imaginary numbers with the concept. He says, let's kind of read this. I'm on page 134 towards the top. Okay, so I'll just read what he says. In this approach, a particle does not have a single history as it would in a classical theory. Instead, it is supposed to follow every possible path in space-time. With each of these histories, there are associated a couple of numbers, one representing the size of the wave, called the amplitude. Okay, I'm going to write that word down. Size of wave, amplitude. And another representing its position in the cycle. Okay, so if I draw a wave, right, where are you in the cycle, right? What position are you in? And so these different places along the wave that you can consider are called the phase, right? Phase. What is that? Where you are. So you're at a high point of the phase or a low point of the phase or in the middle, right? Where you are in the wave. Okay, so the amplitude and the phase are the two numbers that you worry about inside of it, inside of a wave function. Okay, so when one actually tries to perform these sums, however, one runs into severe technical problems. The only way around these is the following peculiar prescription. One must add up the waves for particle histories that are not in the real time that you and I experience, but take place in what is called imaginary time. Okay, so one more time, this is what we want to talk about. Imaginary time may sound like science fiction, but it is in fact a well-defined mathematical concept. And then he goes ahead and explains it to you. 2 times 2 is 4, but -2 times negative, so 2 times 2 equals 4, but so is -2 times -2. That's also 4. But 2i times 2i is -4. So that's he's introducing people to the concept of negative time, imaginary numbers, okay? To avoid the technical difficulty with Feynman's sum over histories, one must use imaginary time. That is to say, for the purposes of the calculation, one must measure time using imaginary numbers rather than real ones. This has an interesting effect on space-time. The distinction between time and space disappears completely, right? So this is the Euclidean idea. Euclidean idea says that space and time behave in a way that's kind of like we're used to with just space, where the Pythagorean theorem holds, right? Flat space-time. Pythagorean theorem. Okay, I can't even read my own writing. Okay, theorem. Pythagorean theorem holds. A squared plus B squared equals C squared. That's a flat space-time, okay? Okay, so a spacetime in which events have imaginary values of the time coordinate is said to be Euclidean after the ancient Greek Euclid, who founded the study of geometry of two-dimensional surfaces. What we now call Euclidean spacetime is very similar, except it has 4 dimensions, right? 4-dimensional spacetime. Oh yeah. There's no time in Euclidean spacetime. There's no difference between the time direction and the directions in space. On the other hand, in real spacetime, in which events are labeled by ordinary real values of the time coordinate, it is easy to tell the difference. The time direction at all points lies within the light cone, and the space direction lies outside. In any case, as far as everyday quantum mechanics is concerned, we may regard our use of imaginary time and Euclidean spacetime as merely a mathematical device. So, and actually, so you know what, he didn't lie then. Remember that in quantum physics, if I give you a plus bi is our wave function, it's a very simple wave function, then psi star is a minus bi. And the way to calculate something is like this, right, which is just psi star psi. And therefore, a plus bi times, a minus bi, I messed up. All right, whatever. You're doing 1 plus and 1 minus. I got them reversed though. This should be first, right? Then you get a squared plus b squared. Okay, you get a positive quantity. All right. So he goes on, we're actually, I want to show you this big world model that he talks about. A second feature that we believe must be part of any ultimate theory is Einstein's idea that the gravitational field is represented by curved space-time. Particles try to follow the nearest thing to a straight path. But because space-time is not flat, their paths appear to be bent, as if by a gravitational field. When we apply Feynman's sum over histories to Einstein's view of gravity, the analog of the history of a particle is now a complete curved space-time that represents the history of the whole universe. To avoid the technical difficulties in actually performing the sum, these curved spacetimes must be taken to be Euclidean. That is, time is imaginary and is indistinguishable from directions in space. So to calculate the probability of finding a real space-time with some certain properties, such as looking the same at every point and in every direction, one adds up the waves associated with all the histories that have that property. Okay, so that's cute. It's a pretty cool trick. We can use imaginary time. So you guys are supposed to know that this is a trick that's used by cosmologists to make time and space to be the same. Okay, so what's funny though is that you end up with a curved surface, and he actually shows you one possible example would be a sphere, right? So here's a sphere, and so on the Earth we have the South Pole, right? The South Pole, and then we have these lines of I'm doing it wrong. Sorry, this way. This is the equator, right? The middle. Make it bolder, right? And then you get gradually closer and you get a North Pole, right? So on the surface of a sphere, we have these special, points right here. And he's saying that if the universe is curved or space-time is curved, that you can get a kind of a similar picture. And so he draws a similar picture, but instead of using this as being the North Pole, he calls this the Big Bang. Right? And the universe expands, right? Why am I drawing them backwards? Because I'm not used to it. Anyways, there's an equator, right? What does that mean? The maximum size. And what's happening is as we go in this direction, imaginary time is increasing, right? And then he has, you know, the possibility, at least, that you can come back together again. And so this point over here, if this is the Big Bang singularity, then this would be the Big Crunch. Now, we don't really think that that's going to happen anymore, but I think it's important to leave in what he managed to think about, right? It was a possibility. All right. So there's some really cool stuff at the end of the chapter about the boundaries and whether or not there needs to be boundaries. I think that would be kind of interesting to talk about. Let's see. Did anybody read about the boundaries? What are the boundaries? Anybody read anything about boundaries?
Yeah, I read it. And about how there might not need to be any boundaries.
That's right. If you use imaginary time, then one of the possibilities is that you could have a universe that doesn't have boundaries. Okay. So he says, this is page 139, right? That if the universe really is such a quantum state, there would be no singularities in the history of the universe in imaginary time, right? That it's just a point on the sphere, but it's not necessary to think of it as a singularity anymore. It's just a point on the sphere, and you can continue going. It really wraps around, right? So there's no finish to this, right? It's a cycle, perhaps, but it doesn't have to be a squished down point where all of space-time is nothing, right? He's saying that with this imaginary time, time is always there, right? And so you never really have a true singularity of space-time because, in fact, the imaginary time can continue along its path. But what does it mean? That the universe could be finite, but without any boundaries or singularity. In our real time, we go back and we see what we would call a singularity. And in the black hole, we have a singularity, but it's not real, right? I mean, it's real to us, but in somehow it's just what we perceive of it. It's not necessarily what the truth of it all is, right? If you could rise above, if you could see the four-dimensional space-time, you would understand that there's no singularities anymore. So there's a perception of singularity. So what does it mean? In this imaginary time, singularities disappear. Right? So even in a black hole, the singularity doesn't have to be there anymore. Now, I think that we still have a problem with spatial singularity, but I'm not going to worry about that. With the quantum mechanical idea, though, then you won't even have a spatial singularity, right? There'll be a finite length, the Planck length, right? There'll be a finite distance that the space-time will be on, and there's nothing smaller than that, right? The Planck length. And so we don't actually ever have a true spatial singularity either, right? So there'll be a Planck length, and then, along the time dimension or the imaginary time dimension, there will be a Planck time, right? Actually, you know what? I don't know if I've ever looked this up with you guys. Have I talked about Planck time before? Anybody?
First time I'm hearing about it.
Okay, cool. Let's see if we can find something on it. Okay. So what is the Planck length? Oh, that's cute. Actually, you know what? I like Wikipedia better. These guys are pretty good though, but look at all the ads. I don't like all the ads. Let's go to Planck time. Okay, in quantum mechanics, the Planck time is a unit of time in the system known as the Planck units. Okay. Oh my gosh, this is so beautiful. Look at this. Oh my gosh. Look at this. Oh my gosh. Don't you just like the names? Can you guys write that down? Lorentz Heaviside, Gaussian. Oh my gosh. Do you guys want to know what those are? Anybody interested? What are these called? Right? Anybody interested?
Yeah, I'm interested.
I mean, what is this? There's two different versions. And what they are actually is two different, oh my gosh, I shouldn't tell you this. You want to hear this? I don't know if you want to hear this. They're not much different, right? They're just slightly different. And these are different, these are, okay. So they're time intervals, they're pretty close to each other. It turns out that there's some slight differences in the units. So there's two different things here, right? There's two different, they're pretty close to each other though. They've got the H bar, the big G, and C to the 5th, and a square root. And this one just has a 4 pi extra. That's the only difference, right? And we talked about this H bar before. Okay, so what are these called? Actually, just so you know, these are called in physics. These are called gauges. A gauge theory. A gauge theory. So we have two different versions that we were shown, right? The two different versions are called Lorentz and Gaussian. And I don't happen to know what the exact differences are, but I can tell you what the concept means, right? So a gauge theory is an idea where it's really like using different units. It's kind of like that. Like it's not just that, but it's like that, right? So how different are we talking? Well, you know, you and I, when we talk about the speed of light, this is an example of one of the gauge transformations that you can do. What's the speed of light? Well, c, right? That's c, and we know it's got a number. It's 3 times 10 to the 8 meters per second, right? We know the speed of light is some number, right? But if you're a theoretical physicist, this number happens to be important, but the number itself is not so important to you. And so there are people out there who say that the speed of light, right, is 1, right? Isn't that cute? No? That's not cute?
It's
Nobody,
cute.
that's cute, right?
Yeah.
You can do this. That's okay. You say the speed of light is 1. It's the unit that we're going to use to compare everything else to. It's a very funny idea, but what it is, it's a gauge theory, part of a gauge theory, right? You can use this as your gauge, right? And it's one of the transformations that you might do, right? So you could do something similar. You could do, you could actually say that the Planck length, even though we call it a very tiny distance, right? You could say that that's a 1 as well. And so there's approaches to the universe. If you're a theoretician, you don't have to be stuck on meters and kilograms and seconds. You can jump to another set of units. And anyways, those are called gauges. Okay, so you could go look them up. I don't know what they are. I mean, actually, this is such a random thing to do, but maybe we should look at this. Let's look at this. Let's see if I'm right. I hope I'm right. This is a system of units within CGS. Oops, I messed up. I didn't mean to do that. They share blah, blah, blah. Oh, here we go. Oh my gosh, it's exactly the one I just told you. So in this system, these values are 1. Well, the square root of 1 over the square root of these numbers is c, and therefore the speed of light is 1. So that's actually what this one is. Okay. So c is 1 in this system. Okay, I got lucky. That's actually what Lorentz Heaviside is doing. Okay. Man, there's a lot of physics, isn't there? Okay, so in Lorentz and actually in Gaussian too, but see in SI, this value is 1 in these two systems apparently. Okay, so both of those systems, it's 1. How about that? Okay. Kind of curious. Actually, Gaussian. anyways, okay, that's not relevant. Let's not forget about that. Okay, so Planck time would be the idea. It's the smallest unit of time. And so there's no singularity possible in space or in time. It's just not possible because there's a minimum kind of distance between any two moments or any two places in space. Okay, so that's a weird idea, but that's something that you get for free from quantum physics, right? That idea that there's no singularities. In space or time, right? They're not possible. And so we just saw because of that Planck length and the Planck time. Okay. Okay, so one can also use, okay, probably, I don't know. Okay, further predictions of the no boundary condition are currently being worked out. A particularly interesting problem is the size of the small departures from uniform density in the early universe that caused the formation first of the galaxies. So again, I think I probably mentioned this a couple of times, but in this day when Stephen Hawking is writing this book, the space-time that he sees, or the microwave background radiation that he sees, is uniform, 2.7 K. And what we see now is that there's tiny little variations on this. So he would be really happy about that, because for him it would be kind of evidence why would the universe form galaxies? You know, why does it have clumps of matter? Why isn't it the same in every direction? And the answer is because there are little variations that occur, right? There are some small changes. Okay, and so the universe would have undergone a period of rapid expansion. The non-uniformities would have been amplified until they were big enough to explain the origin of the structures we observe around us. Okay, blah, 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 blah. Okay, the idea that space and time may form a closed surface without a boundary also has profound implications for the role of God in the affairs of the universe. With the success of scientific theories in describing events, most people have come to believe that God allows the universe to evolve according to a set of laws and does not intervene in the universe to break these laws. However, the laws do not tell us what the universe should have looked like when it started. It would still be up to God to wind up the clockwork, and choose how to start it off. So long as the universe had a beginning, we could suppose it had a creator. But if the universe is really completely self-contained, having no boundary or edge, it would have neither beginning nor end. It would simply be. What place then for a creator? Okay, so I'm going to ask you guys a question. Do you think that Stephen Hawking believes in God?
I was just thinking, I wish I could ask him the same question.
What was that?
I was just thinking about, like, if he did or not, and then you wouldn't ask that.
Okay,
I don't
so
think
that's the question, right? He says, do you need a God anymore, right? So I'm just wondering, do you know anymore? Does anybody know if he was believed in God or not? Anybody know?
I don't think he did.
No.
I watched a movie that's based on his life called The Theory of Everything.
Uh-huh.
And
Yeah.
in that it seemed like by the end of his life, or whenever he figured his stuff out, that he didn't seem to believe in a God, and that was something that conflicted with his wife's views.
Mm-hmm. Okay.
he was very into, like, being able to find a math theorem that could explain everything at once.
Right.
It seemed like his version of God was just like the ultimate law.
Uh-huh. Right. Well, that was the focus of his life, right? This concept that there could be a way to combine everything that we see into a single theory of the universe. And I mean, that's actually something that we're going to continue trying to look for. In fact, actually what's coming up, there's a really fun part of our course where we start considering string theory. And And string theory has incredible possibilities. It's still a little bit difficult to call it science, and we'll understand why. Actually, do you know why? Does anybody know why already? Maybe you know why. String theory is difficult to call a science. So it's something to think about. Well, then I don't want to tell you now. Then if you don't know, we'll just wait and see. But there are some really beautiful ideas. But the question is, if it's science, I guess I'm giving it away. If it's a science, then one of the requirements of science is that you test it. So no matter what, a scientific theory is only scientific if you can test it, and it has the possibility to be wrong. So if you can never test a theory, is it a scientific theory?
No, it's more like
It is not a scientific theory. No, it is not, right? If you cannot test it, if you cannot say, you know, I've checked, I have a hypothesis and I'm going to check my hypothesis. If you can't do that, then it's not a real scientific theory. So we have an issue. Well, you know, I mean, it's something that will come up against in the near future. But anyways, to think about. So I will be posting a quiz for you based on today's lecture and our topics. You should have finished chapter 8, and I'm actually still planning on writing individual quizzes for chapter 8 and chapter 7, and maybe, I don't know if I'll go back further than that. But what you should be doing next is reading chapter 9 for Wednesday. And chapter 9 is a really fun chapter because it's a very short chapter, by the way. So please take good notes. How do I give you guys a quiz before class? I could give you a quiz before class, huh? How many people would like that? Anybody like that? Quiz before class? Before class starts? Anybody like that? Huh? You want it after? Okay. Okay, so the next chapter, chapter 9, is on the arrow of time. Okay. And you'll learn that, has anybody read chapter 9 already?
Not yet.
Not yet. Okay. So you'll learn that there's actually, well, anyways, I'm not going to say then. Okay. So there's an arrow of time. All right. And yeah, we have some really fun stuff coming up. The arrow of time will take us to the next topic. And then, you know, we'll continue from there. Okay. So I actually, I'm thinking about some other alternatives. So you guys have today what you're going to be doing for your half of your points will be to take a quiz, and the other half would be to post a discussion question or a response to a discussion question. Okay, so I'll write that up for you in your participation for today. But you can go ahead if you have anything, any questions or ideas that you want to talk about. The goal would be to try to have a place to discuss some of these ideas. And instead of just me talking, would be to allow you guys to talk a little bit more. Okay, and I think I would have done that if we were in a classroom. But all right, so have a great day, and we'll see you guys on Wednesday.
All right, thanks, Professor. Have a great day.
Thank you. Bye.
Thank you.
Bye.